Hello, I am Vijay Kristipati. I would like to give the presentation on two important peer-to-peer system protocols. First one is Chord, a scalable peer-to-peer lookup service, and second one is Vivaldi, a decentralized network coordinate system. I am giving the presentation based on the slides prepared by the authors and other presenters. Chord protocol. Before I talk about the Chord protocol, I would like to discuss about the motivation behind the Chord protocol. Let's take an example. How can we find the data in the distributed file system? Let's assume that there are 5 nodes in the system: N1, N2, N3, N4 and N5. Now N1 wants to store a file in this file sharing system. With the key let it be, and the value would be actual MP3 data. And now when N5 wants to find the file with the key let it be, how can it knows that node N1 has this let it be file? There are a couple of solutions in the currently peer-to-peer systems. The first one is a central server system, which is used by Napster. In the central server system, now the node N1 will go and insert a record in the database saying that, hey, I have a MP3 data with the key let it be, and here is my IP address. Now if any other node wants to find the system, say N5, it goes and queries the database saying that, give me the IP address of the node with the key let it be. And now database replies back saying that, N1 is a node with IP address so and so. There are two issues with this centralized solution system. The first one being the state maintenance. If there are M messages in the whole system, the database has to maintain big O of M state in the worst case. That's a huge state. And now another problem is single point of failure. If the database dies, there is no way that N5 can find that node N1 contains the key let it be. There is other solution used by Nutella and other peer-to-peer systems, which is flooding. In the flooding scenario, if N5 wants to find the file with the key let it be, it floods this request to all the nodes in the distributed systems. It goes and makes a request to N3 and N2, N4 and N1. Now N1 replies back saying that, hey, I have the file with the key let it be. The main problem with this flooding system is the message lookup. In the worst case, if there are n nodes, there should be big O of n messages has to be sent to all the nodes. In the centralized server, the big problem is the state maintenance, which is big O of m, and in the flooding system, the problem is the lookup, which is big O of m. So the authors decided to make the best of those two and came up with a Chord protocol. The basic Chord protocol gives us a couple of things. The first thing is to map the key to a particular location. Right? If I have the key let it be, this key maps to which location, and in that case it's N1. So it maps keys to the location. Now it has to accommodate the nodes joining the system. If new nodes join the system, how can it accommodate that? And if a node's failures or leaves intentionally, how should this the Chord system will accommodate that? So this Chord protocol satisfies these three important things. Authors also claims a couple of important properties. Author says that it is very simple. It doesn't really use the complex algorithm to calculate these keys to location, and very efficient lookup, which is big O of log n messages. Coming back to flooding system, it's big O of n messages, but the author claims that Chord protocol uses only big O of log n message per lookup, right? So it's like a binary search. And then it's a very scalable. It has to maintain only the state of big O of log n state per each node. Coming back to the centralized server, it has to use big O of m messages. And it is a very robust. it has to survive massive changes in the membership. If a node leaves the system or if the nodes join the system, it maintains the whole state without any issues. Coming back to the central system, if the server fails, then it's very hard to get the data to retrieve the data from the database. Proofs of this big of login messages and scalable of big of login are in the papers. I'm not going to talk about more details, but these are a couple of important chord properties to remember. Now let's go a little bit detail of the key storage mechanism in the chord system. Let's consider a circle with 0 to 7 as an identifiers, right? It could be a keys or it could be a nodes. Now let's assume that there are 3 nodes in the system: 0, 1 and 3. And now we want to understand how keys are stored in these nodes. Now let's take an example of key 1. The way that chord protocol stores the keys is using basically a formula. The successor of the key should be stored in the next highest node. So in this case, successor of the key should be stored in the next highest node, which is 1. So the key 1 will be stored in node 1. Now let's take another example. Key 2. Successor of key 2 should be stored in the next highest node, which is node 3 in this case, and it should be stored in the node 3. So the key is stored in node 3. Now let's take another example. Key 6. Again, going back to the same thing. The successor of the key 6 should be stored in the next highest node, which is node 0 in this case, so it is stored in the node 0. So this is how the keys are stored. The chord uses the another protocol called consistent hashing to store the keys into that location and maps the keys to the location, but it uses some optimizations which I'm going to talk a little bit later to make this key lookup faster. So having understood that the way that keys are stored and are mapped into the location, now let's understand how the node joins and node departures affects this key storage. Now let's assume that node 7 joins into our system. As we discussed earlier, the successor of the key should be stored in the next highest node. Previously, the successor of the key 6 is the next highest node, node 0. That's why we stored the key 6 in node 0. Now node 7 joined, so it has to be stored in the node 7. So as soon as the node 7 joins into the system, key 6 will be moved back to the node 6, node 7. So the key 6 is moved back to the node 7. This is how node shuffling, key shuffling happens when node joins into our system. Now let's assume node 1 depart from our system. So if the node 1 departs from the system, the successor of the key 1 should be placed into the next highest node, which is node 3 in this case. So the key 1 will be moved to the node 3. So when the node departs or node joins, there would be a key shuffling so that we can easily map the key to the location. So the chord protocol gives us the simple, elegant mechanism to map the key to the location. It has to store only a very, very small amount of routing information, which is its successor of that key, right? If we know if each node maintain its successor, it can move back into that circle. If you can imagine that nodes are placed in the circle, it moves back into the circle and finally maps key to the location. But there is a big problem, which is an efficiency, right? That's the whole point we start. If it might take big O of n, right, in the worst case, to map the key to the location. Node 0 maps to node 1 and node 1 moves to node 2, node 3. So it might take big O of n messages. So the author came up with some efficient lookup mechanism. In order to make this lookups efficient, we need to maintain a little bit more data, right? If we maintain the whole nodes information, then the state is big O of n, which is what we discussed in central server. If you maintain only one node, it takes big O of n again, but less amount of data. So the author came up with a little bit of more intelligent formula to put the state in, in a way such that it doesn't take big O of n state. So that the state is small, at the same time lookups are efficient. The data that are stored in each node is stored in a particular table called finger table. So a finger table maintains the state of particular node, so that it uses that state for efficient lookup to make the lookups to be a big of log n. The formula they came up is n plus 2 power I minus 1 arithmetic log mod 2. So they uses this formula to find the successor, right? So the data they maintain in the state is pretty much n plus 2 power I mod m being the identifier. We can talk a little bit more detail in the next slide, but the point here is each node maintain just not one information which is successor, but it maintains some data in the finger table, so that the efficient lookups are possible to get the achieve big O of log n state. Now let's go back and look at the same our example with the finger table. Now instead of node 0 just having the successor 1, it maintains some other information in its finger table. It maintains the key 6 as we have seen example before, and it also maintains some other information, which is it maintains the state of node 1, node 2 and key 4. So it maintains the key 1, key 2, key 4 information. So the way it calculates is 0 being n plus 2 power I mod m being the identifiers. Here number of identifiers are 8. So the way it calculates is node 0, so 0 plus 2 power I 0, 0 plus 2 power 0, 1 mod m identifiers, 8 identifiers here, 1 mod 8 is 1. That's why it stores 1. Now it stores again 0 plus, now the next node is 1, 2 power 1 is 2, so 0 plus 2 is 2, 2 mod 8, 8 being the number of identifiers here 8, so 2 mod 8 is 2, same as 2. Now again takes another example. It maintains 0 plus 2 square, which is 4, 0 plus 4 mod 8 is again 4. So it maintains the information of 1, 2 and 4, and it maintains its successors. So the key 1 successor is 1, key 2 successor is 3, and again key 4 successor is 0. So it maintains this keys information. Previously it just used to maintain only one key, which is it maintains the 6. Now it maintains some other information of the other keys, right? The key 1 is stored in node 1, key 2 is stored in node 3, key 4 successor is stored in node 0. Same thing with the other nodes. So each node maintains its finger table, as the formula that they use is n plus 2 power I mod m being the identifier. So it stores these keys and and other finger table. This is just a text of what I explained here, but the thing is, important thing over here is there could be a possibility that the node has to move to get the key information is not available immediately in that node, because it just maintains only small set of keys information in its finger table, but it has to make the query to the next node to get the key information, and finally it can retrieve the key information. So the amount of travel it has to make is not big O of n in this case, it is big O of log n, because it maintains some information, so it gets big O of log n messages. Now let's see how the node joins and node departures with the finger table affects. So go back to our example again. Now node 0, node 1 and node 3 maintains this finger table. Now let's assume that node 6 joins into our system. If node 6 joins to the system, node 6, once it joins, it has to load its finger table information such that it has it can makes the lookups fast. Right, it gets this information through some other node, maybe node 7. It makes the node 3 and gets that information, and has all the info, its finger table loaded. It's loaded its finger table. And now once it loads its finger table, it goes and makes a call to each node that it has in the finger table, and then it updates its keys of those tables. It gets the key shuffling happens as we have seen, and also each finger table's data has been updated. So this is how it affects. And now when the node departs in the system, same thing, the key shuffling happens. Key 1 moves to the node 3, and then finger table gets updated. So it takes some time to get this finger table updates, but it eventually all the finger tables are updated. But there is another problem with this system, right? I have just shown one node joining and one node leaving. What happens if multiple nodes joins at the same time and multiple nodes leaves at the same time, right? It gets some time to get this finger table gets updated. But if you can remember the basic point, the first basic chord protocol, if we can maintain just its successor and predecessor properly, it works, right? It might take more time, big of n, but eventually it works. It gets that it can maps the keys to the location. After some time, the finger table gets again populated properly, and the acceleration lookups can happen. So it works with the concurrent operations because it maintains the successors and predecessors properly, but the finger tables maybe need to be fixed. After some point, again it gets to the big of n, log n messages lookups. In order to maintain this, each node has to run some stabilization protocol so that it maintains its predecessors and successors properly. Right? Let's see how the stabilization protocol will work if a node joins. In this scenario, ns is the node successor and np is the node predecessor. Now node n joins. Once the node n joins, it doesn't know its predecessor, right? So it makes its predecessor to be null. And now n knows its successor through some other mechanism, maybe n2 or something like that. So it updates its successor and sends a message to its successor saying that, hey, I am your new predecessor. So now n sends a message to ns saying that I am its new predecessor. After receiving this message, ns change its predecessor from np to n. So this is how it changes. Now NP runs a stabilization protocol after some point, right? Saying that, hey, what is your new predecessor? NS replies saying back that my new predecessor is N. Now NP knows that there is another node joined because it was assuming that NS predecessor is NP, but NS replied saying back that it's N as its predecessor. Now NP changes its successor to N, and it sends a message saying that I am your new predecessor. Now N changes its pointer from nil to NP. So this is how the stabilization protocol will work. All the predecessors and successors have been fixed now, but the finger tables has to be fixed. It will be fixed during the course of time. But as long as we maintain its predecessor and successor information, it can ask the question to next node, to next node, to the next node, so that it eventually maps the keys to the location. So in order to recover from failures, concurrent failures, each node maintains a list of its successors and predecessors in separately. So if one of its successor node failed, it goes back to the next successor. It can go back to the next successor. The successor that succeeded will be its live entry, and after some point, all these finger tables and nodes, predecessor and successors are fixed again, so that the lookouts again will become accelerated, and then it becomes big of log n. So this is how the chord protocol works at a very high level, and I hope you enjoyed my chord protocol presentation. Now let me talk about another important peer-to-peer system protocol, which is Vivaldi. What's the Vivaldi? Vivaldi is a simple, adaptive, distributed algorithm I will go in detail why it is simple, why it is adaptive, and why it is a distributed algorithm. And the main purpose of its Vivaldi is to calculate network coordinates between the two nodes so that those distances maps to the RTT. Right, the distance between two nodes is equivalent to RTT, round trip time of those two nodes. The way it calculates is it assumes all these internet hosts to be in some geographical coordinate space, and then it calculates the distance between those two nodes. The distances between those two nodes is equal to, basically the round trip time of those two nodes. Now let me explain you why we wanted to predict RTT instead of calculating the instead of sending a ping message and get measured RTT. Right, why do we really want to uh, uh, calculate RTT without really pinging and accurately measuring RTT? Let's take an example, another peer-to-peer system, BitTorrent. I know most of you knows BitTorrent's peer-to-peer system and how it works, but I will go at a very high level details. Let's assume that I wanted to store a file in this BitTorrent system. I'll create a BitTorrent file and put it in the search engine. And now if somebody somehow through third-party mechanism, they know that my file is in this BitTorrent system. So he goes and makes a query to torrent search engine and downloads a torrent file. This torrent file contains the information about the tracker. So the user will go and query the tracker. The tracker coordinates the list of the nodes that contains the file that I uploaded. Right, so it gives this information to the user. Node n1 to node n contains this file. Now user wants to just query one node and gets the data. Which node he has to go and make the query to get the file? Obviously he has to go and get the file from the node that is closest to system, right, to his node. Right, he doesn't want to make the cross continental or cross ocean, right, to get the data because the round trip is fast. But he doesn't want to go and ping all the nodes for that particular file. Right, that takes a lot of time. And in this case, Vivaldi comes into the picture. If somehow his computer runs this Vivaldi algorithm, and then all other nodes also runs the Vivaldi algorithm, then he can easily identify the node that is closest to the system without really measuring the RTT. Right? This is one example where we want to calculate the estimate RTT without really going and pinging all the nodes and finding out which node has the lowest latency. There could be a lot of examples like Chord in the Chord protocol that I gave earlier. Also, we wanted to find if the key is mapped to the multiple locations, we wanted to find out which node in that circle is closest, right? So there are other examples why we need to measure RTT without really measuring the RTT. Why do we need to calculate the RTT? Having understood that we want to calculate RTT without really measuring the distance RTT, let's see how this Vivaldi algorithm works in action. Again, going back to the statement again. So the way that Vivaldi algorithm works is it positions these nodes in some coordinate space in such a way that distance between those two nodes is equivalent to the RTT between those two nodes. So if there are nodes n1 to n5, distance between node n1 to n2 is equal to the RTT between node n1 to n2. Can we really measure something like this? No, probably not. Reason being, it violates one of the basic mathematical formula, which is triangular inequality. Let's go talk about a little bit of triangular inequality. Let's put these nodes in a triangle, n1, n2 and n3, and the distances are a, b, c respectively. We know from the triangular inequality, like distance between a should be less than or equal to distance between b and c. Right, a should be less than or equivalent to b and c. That is the triangular inequality. Can we have this triangular inequality in our networking systems? Let's take an example. Let's see that the RTT between node n1 to n3 is equal to 100 milliseconds, and node n1 to n2 is 48 milliseconds, and node n3 to n2 is 48 milliseconds. According to the triangular inequality, 100 should be less than or equal to 48 plus 48, which is 96. Is that true? No. Why can this happen? We know that from basic 101 networking, we have a different physical medium between the nodes, right? And the distance between N1 and N3 might be a Cat3 cable or Cat5 cable, and N1 to N2 is the fiber optics, right? So that because of the different physical medium, there could be a different latencies, right? So we cannot achieve this triangular inequality. So the goal of this Vivaldi algorithm is pretty much we wanted to try to minimize the error so that the distances are equivalent to the RTT. So we need to move the nodes in such a way that it goes and accurately models to the as much as to the triangular inequality, so that if we can predict the distances to that RTT. If we can do that, then we are minimizing the error function. And then we can accurately map the RTT to distances to that RTT. In order to minimize this error, author chooses some particular formula which is more or less applies to the real life system, which is a spring system. So we know that the energy stored in any spring system is equivalent to some constant times the square of the displacement, right? In the way that we are talking about, that if we can move the nodes in such a way that distances maps to the RTT. Same thing, if we move in a spring system, if we move each spring so that we wanted to minimize the energy in the whole spring system. And this is the formula, right? Square of the initial distance minus of the displaced distance to the square for each spring among all the nodes. And Lij is the actual RTT between node J and node I, and Xj is the node J, synthetic coordinates at I, and Xj is the synthetic coordinates at J. So if we can imagine that these are all the nodes, or these are all the springs, the distances between if you move these springs, each spring in such a way that the total energy stored in this spring is less, or if we translate to our to our system, where these are all the nodes, we move to nodes in each direction. We displace this one, we displace this one in such a way that energy is in the case of spring system, and error is our system, right? So that the energy is less or error is less. As long as we can do that, as all the nodes are moved, in the final moment, all the nodes predicts the distances to the RTT. So the author chooses this particular function. He could have chosen some other particular function and then come up with a different formula. But he chooses this function because it really applies to our physical spring mass system. And from this energy mass system, from this spring system, we know the Hooke's law, right? If we move any spring to and then put a force, then we know that there is a restorative force acting in opposite direction. So the restorative force is nothing but the direction it moves. This is the direction it moves times the displacement, the initial displacement minus the final displacement. So if the restorative force is nothing but the error, right? If we calculated the restorative force, we are calculating the error. So this is again another important formula which will be used in our Vivaldi. And this is just a spring analogy, where if we initial rest position is 5 meters, and then once we displace it, it goes to 8 meters. So the displacement is 9 minus 5, which is 3, of square, which is 9. So just an example. Now let's see in action how we can move each node such that distances are equivalent to the RTT. Let's assume that we put a pressure or force on this node. As soon as this node moves, immediately this node gets moved, right? We have seen that in a spring system, one spring moves, the other spring moves. Since this node moves here, now this node gets moved. So it gets moved here. Now since this node is moved, this node is going to move, and now this node is going to move. So as every node moves, so that after a final convergence, the distances are moved so that the distances represents the RTT. This is how the base Vivaldi algorithm works. Let's see in a centralized version where we have the latency matrices of all the nodes, right? But in reality we might not have all the nodes. We just know the RTT of one node, right? We don't know the whole RTT of all the system, right? Because that's what we want to calculate. Now let's see how this algorithm works. Since we have the latencies of all the nodes and we wanted to find the we want to move one node, which is x in this case. Let's say that initially the force is 0 and now we wanted to calculate the force. In order to calculate the force is nothing but the force or error is equal to Hooke's law, which is nothing but the initial displacement, initial distance minus the final displacement is equivalent to the force factor, right? If so, E is equal to initial RTT minus the displaced RTT, xi minus xj. Xi is the current position and xj is the current position of xj. So we move xi, we minus the xi minus xj with the initial thing, and then we add it back to the force vector, which is 0 in this case. So F is equal to F plus E, which is what we calculated, times the direction, some constant direction. So we moved either in upward or right, left or right, or up or down. And then we move to a small step with some time interval, and then we move. But again, this is a central algorithm which we use this as a base version to calculate our Vivaldi. So we calculate the net force, we moved in the direction of net force. Let's take a simple Vivaldi algorithm. In the simple Vivaldi algorithm, as I explained, we don't know the latency of all the nodes. We just know the latency of one particular node, which is xj. So we know that RTT of that node. So we calculate the error function in the same as this what I have shown earlier. So RTT minus xi minus xj, and we wanted to move to direction of the force, which is either right side or left side, or in our iterative example we have seen that moving up, down, right or left, and then we calculate the direction and we calculate the force. Now the movement that xi makes is equal to previous xi plus delta, which is some constant, times that force. So xi moves into that direction. So since this xi moved, now we will calculate xn, xt. So that's how we calculate all the nodes. This is a distributed algorithm because it runs on the same algorithm on every node in the peer-to-peer system. So it's a distributed algorithm. Here we made this delta as some constant, right? With this delta making some constant, there are some issues here, right? If we make this delta a little bit smaller, then this node moves slowly and takes a lot of time to get converged. If you make this delta a little bit larger, it moves back and forth, and finally it gets converged. That's the time it takes to converge. It depends upon the delta constant. And the next issue is we are assuming that this xj is that claiming the xj is claiming its distances correctly. What happens if the node xj is new to the system and it doesn't really accurately knows it has to move, because still it doesn't, some other nodes adjacent to it might be moving, so it might has to change its node distances. So we are not really calculating its node's distance. We are assuming that that distance is correct and we are calculating it. So it might take again a huge time to get converged. So taking this simple Vivaldi algorithm, authors came up with the adaptive algorithm. In this adaptive algorithm, this remote node also tells about its error factor, how much it thinks this node position is correct, its distances, its coordinates are correct. And then we don't really directly takes this xj as the distances, but we calculate the remote node's error also into the factor. So this weighted balances, sample weighted balance, is nothing but its local error by local error plus remote error. With this formula, if the remote error is small, then we just take that as correct and then we move according to the remote node. But if the remote node is large, then we don't really consider that distances xj as, we don't give big factor to that. So this is a good example of moving according to that the remote node's error and remote node's distances, and then we calculate the relative error, and then we move after the calculation of the relative error and the weighted balance. And then in this case we don't calculate that, we don't assume a delta like 0.01. We calculate the delta according to the local and remote errors, and then we move in that way. Right? It's the same formula, but the basic difference is previously delta was assumed something like some constant. In this case, delta is calculating. So now we wanted to see whether the Vivaldi algorithm, whether the simple is can be sufficient, or we wanted to use the adaptive step, or actually this Vivaldi algorithm itself works or not. In order to do this, author came up with some evaluation methodology. They calculated some RTTs, and they measured some RTTs, and they calculated some RTTs, and using some topologies, and with 192 nodes and 1740 internet DNS servers, and they calculated all this data, and they drew the graphs. Let's take an example of this, the impact of adaptive type step. Whether the simple Vivaldi works, or we really need to have adaptive algorithm, and if we need it, how much time this adaptive algorithm gets converged when it compares to the simple Vivaldi. The first graph is the simple Vivaldi algorithm, and second graph is the adaptive algorithm. In simple Vivaldi algorithm, there are some different constants of the delta. Right here, delta is calculated. Here, delta is assumed. Here, no matter what the delta is, it takes some time to get converged. If you see here, it's taking 60 seconds to get converged because we are assuming the delta. In this case, delta is calculated, right, because of the remote or local errors, and it gets converged pretty much around 30 to 40 seconds. Between 30 and 40 seconds, it gets converged. Definitely, this graph shows that adaptive algorithm gets converges pretty fast. Now, let's see another graph. When new nodes are introduced, how this simple and adaptive algorithm works. So it's basically robustness to high error nodes. We have like 200 nodes, and every node, and whether you're using the simple Vivaldi or adaptive algorithm, all these nodes gets converged. After this convergence, we wanted to introduce 200 more nodes and see how these nodes behave. With a constant delta in the first graph, we see that at the time 50 seconds after we introduce, all the nodes gets knocked away and it gets dispersed, and then it takes slowly to get it converged. Coming back to the second graph, which is adaptive algorithms, nodes are not really knocked away all the way, and gets the convergence is also fast. If you see this graph here, this one is the constant algorithm or simple algorithm. It's take almost like 300 seconds to get converged back after the introduction of new nodes. Coming back to the adaptive algorithm, it gets converged at the time t is equal to 60 seconds. So definitely this proves that our Vivaldi adaptive algorithm works very robustly compared to the simple algorithm. Now author wants to compare whether this Vivaldi algorithm, even the adaptive algorithm, measures accurately when it compares to other existing network coordinate systems. And they compared with the known GNP, global net position. Global net position is another network coordinate system, but it uses the infrastructure. But with the Vivaldi, we don't use the infrastructure, right? So when we compare it on both of these graphs, we have seen that Vivaldi works superior or at least equivalent to the GNP. So definitely Vivaldi takes an advantage because it does not require an infrastructure, and it measures more or less equivalent to the existing network coordinate systems. So the conclusion, it is a simple, we have seen that, right? It's a very simple algorithm. It just calculates the error or the force, restorative force, and it's adaptive. We have seen that, right? Basically, it's adaptive time step. It calculates that, and based on the remote error and the local error, and a decentralized algorithm. It runs on all the nodes so that we can accurately nodes moves to converges to a certain position, so that we can map the distances to the RTT. And we don't need any infrastructure. Like a GNP requires the infrastructure, but here we don't need any infrastructure. All the nodes come into the picture, they move. Once a node comes into the picture, it calculates its distances based on the previous node, and then it moves accordingly and then gets its position. And it's a fast convergence. We have seen that with the adaptive algorithm, it really converges fast. And we have seen that even with the new nodes join, right, it gets really converge very fast. And this is how the Vivaldi algorithm works, and we can use this Vivaldi algorithm in other distributed system protocols like BitTorrent or Chord or any other protocols. Hope you enjoyed my presentation. Thank you.